All right, good evening everyone. My name is Melanie Kwong from Public Programs, and I would like to welcome you to today's program, Mars Direct, Humans to the Red Planet Within a Decade. Dr. Robert Zubrin, formerly a staff engineer at Lockheed Martin Astronautics in Denver, is now president of his own company, Pioneer Astronautics. In the 1990s, Dr. Robert Zubrin proposed the Mars Direct mission architecture using conventional rockets and Mars in situ resources to establish a sustained human presence on Mars. Now, with interest in Mars at an all-time high, the Mars Direct plan is more relevant than ever. Please welcome Dr. Robert Zubrin.
Okay, well, thank you for that kind introduction, and thank to all of you for turning out to hear what I have to say, and for your interest in this subject more broadly, because I think the future will thank you for your interest in this subject more broadly. 25 years ago, early 90s, there were books coming out with titles like The End of History, The End of Science, everything important has already been done, everything worth knowing is already known. It was a good run, it was a lot of fun. Sorry you missed it. You could read about it in the library. We weren't at the end of history or the end of knowledge in the 1990s. And in fact, if we look at the period that we've just gone through in terms of this, and which more or less corresponds to most of my career, it's really been a remarkable thing. And I'm talking in particular with respect to space. In 1990, we launched the Hubble Space Telescope. It was defective, but we fixed it and upgraded it, and it made incredible discoveries, and the other great observatories, and have made fantastic discoveries. Hubble discovered that there's actually a fifth force in the universe beyond the four that I learned about in graduate school, which is causing the universe to expand at an accelerating rate, which is impossible if the only forces were the ones that had been defined earlier. Gravity, and electrodynamics, and the nuclear force, and the weak force. And of course, most notably and most recently, we've had the Kepler Space Telescope, which has discovered thousands of planets orbiting stars other than our own. Until the very end of the 1980s, we didn't know about a single extrasolar planet. Now we know about thousands. And I just attended a month ago a lecture given by Sarah Seeger, an astronomer, summarizing the results of the Kepler mission. And the last slide says, on the basis of these results, we now conclude that 1 in 5 stars has an Earth-like planet in its habitable zone. 1 in 5. Okay, that's 80 billion such planets in the Milky Way galaxy alone. Okay, that's incredible. And then the NASA Planetary Exploration Program has produced fantastic results with the, we already had some hint that Mars was a warm and wet planet from the Viking mission in 1976, but in the 90s we found not only some dried up riverbeds, but dried up lakes and northern ocean, and then the rovers found the salt deposits left by the retreat of the oceans, and more evidence, and detecting continent-sized regions of Mars that are 60% water by weight in the soil. And yes, we've also discovered water in the lunar polar craters that are shadowed. And then this year, the European Mars Express satellite discovered an underground lake on Mars. Liquid water, salt water, but liquid water underground on Mars. And if there's one, there's many more. And this is a place where life could still exist on Mars, potentially. And the American Mars Reconnaissance Orbiter, also using ground-penetrating radar, this is a technique that has been around for a while but has finally come of age, discovered glaciers on Mars in the northern hemisphere. Massive glaciers, glaciers that extend as far south as 38 degrees north, which is the latitude of San Francisco in our own country, so well south of you. And these are glaciers that are covered only by a meter or so of dust. They are within shovel distance of the surface. And the size of these glaciers are incredible. They are so big that if they were melted and you spread the water out, it would cover the entire planet Mars with a layer of water 3 feet deep. Just these glaciers. There's more water than that on Mars, but just these glaciers alone. They're gigantic. Okay, they're comparable to the amount of water there is in North America. The amount of fresh water in North America. Yeah, okay. Well, that's been the two productive parts of NASA, which is the space astronomy and planetary exploration program. Now, there's been floundering in two other important parts of NASA, the part that's supposed to achieve cheap space launch and the part that is human exploration, have not achieved very much at all in my whole career in aerospace. From the 1980s to today, there's been, NASA achieved no advance in space launch, zero, and the human spaceflight program has been stuck in low Earth orbit, with its only significant achievement being its support of the Hubble Space Telescope program. Now, that's not to say that humans cannot do good things in space. In fact, Hubble proves that they can. Those were 5 shuttle missions out of 130. If all 130 shuttle missions had been equally productive, it would be the greatest science program in human history. But unfortunately, it was only a tiny fraction of the shuttle missions were well conceived in terms of actually having clear objectives, very defensible objectives. But precisely this failure on the part of the space launch and human exploration parts of NASA has provoked a solution coming from a different direction altogether. That is, from the direction of the entrepreneurial space companies. SpaceX, Blue Origin. Space, of course, is the most notable. There's several others, too. But to be clear, I mean, in the 1960s, when NASA was storming heaven, no one would think we need entrepreneurial space companies, okay? There was no need. NASA was doing it. Fantastic job. But in the period after that, it has stagnated, and eventually, in the 90s, people started to attempt to do this on their own. Those were weak efforts at first, but finally, after the turn of the century, we started to see more muscular and successful efforts, and so you have SpaceX. And to be clear, what SpaceX has done is incredible. They have proven that it is possible for an entrepreneurial organization to do things that previously been thought that only governments of major powers could do. And not only that, do them in 1/3 the time at 1/10 the cost that have been considered normative. And not only that, but do things that have been considered impossible altogether, such as taking the launch vehicle and bringing it right back to the pad and landing it right there. Okay, reusable launch vehicles been written off as just, no, that's science fiction. There it is, science fact. It's happening, and creating thereby some very valuable capabilities, as we'll discuss, that could help get us to Mars, but doing something even bigger than that, which is, well, as I say, prove that these things that had previously been considered intractable technical problems were really institutional problems. And so, as a result of what Musk did, a whole raft of entrepreneurial space companies have been funded, including people, not just the Jeff Bezos of the world who could fund themselves. There are people I know, friends of mine, who've gotten $70 million worth of funding to create a small launch vehicle, and this kind of thing. Do people with individual means know more than most of you? But they've gotten this kind of investment. And this is happening. And not only that, but even people in fields outside of space launch. For instance, there are now fusion power startups getting funded. Fusion power has been one of these things like cheap space launch. Yeah, it'll happen someday. Yeah, I've heard that for a couple of decades now. But now people are saying, well, maybe the problem with fusion power isn't that it's an insolvable technical problem. Maybe it was an institutional problem. And you have startups getting funded with very serious money, $100 million, $200 million, in one case, $500 million. Okay? And I myself, I actually worked in the fusion program in the 80s before I started working in space. And at Los Alamos. And I can remember one lunch we had in my group where the group leader sat down and he says to us, you know, when fusion power is finally developed, it's not going to be by at a place like Los Alamos or the Livermore lab. It's going to be by a crackpot working in his garage. Well, I don't think it's going to be a crackpot in his garage, but a startup in a warehouse, yeah. Okay, so this has been unleashed, and tremendous creative forces have been unleashed, which now pretends the beginning of history. So we're not living at the end of history. We're living at the beginning of history. And the beginning of history, as the future will see it, is humanity's move out from its cradle planet into the broader universe. Because we're living in a universe of billions of habitable planets. Okay? This is our cradle. This is just a tiny part of the real world that awaits us. And I think that we are now prepared to take this step. Now, I'm going to show you a plan that I developed together with some other engineers at the Martin Company, where I was employed in the early 90s. And it has been resting there as a challenge, as an open challenge that you could do Mars if you really want to. Here's how you could do it. Now that challenge was not taken up, but we are now seeing capabilities brought into being that could readily realize it. So the plan is known as Mars Direct, and humans to the red planet within a decade. Now let's just talk about that for a second. How can we really talk about sending people to Mars in a decade? If you have followed this subject, you've probably seen illustrations like this. This is a NASA concept for sending humans to Mars. And you can see, those of you who go to the movies can obviously recognize the heritage. It's based on the Imperial Star Destroyer. And it's quite large. Mars is right there for scale. And it's going to Mars with a gigantic nuclear reactor, 100,000 kilowatt space nuclear reactor. The largest space nuclear reactor that has ever flown is 10 kilowatts. But there it is, and it's using a plasma drive and so forth. And obviously, if this is how we're going to Mars, we're not going there in 10 years. Okay. And to say nothing of the fact that not only do you have to build the Star Destroyer, you have to build the orbiting spaceports to service and even construct on orbit the Star Destroyer and all this. This is just not happening. And this is not a plan to send humans to Mars. This is sizzle for the state being keep NASA funded, and here's the vision of what we'll do someday. Okay, this is not a serious plan at all. Someday we will have giant science fiction spaceships, but just stay tuned. Now, however, going to Mars does not require building giant science fiction spaceships. going to Mars is but not about realizing the dream of the spaceship. It is about sending packages, sending a payload from the surface of the Earth to the surface of Mars that is capable of supporting a small group of people, and then sending either that or a comparable payload back. So how can we do this? By the way, so I'm going to lay out the plan, and obviously in a talk of an hour, I cannot explain every part of this in adequate detail. But I have written a book on the subject. And if after this talk you think I know what I'm talking about and you want to read more, we've got a bunch of them over there. You buy them, I'll sign them. It's a win-win situation. There it is. But what is the plan? Okay, we do need a heavy lift vehicle. Now, heavy lift vehicles are not science fiction. In fact, well, that was 1969 you're looking at there. Half century ago, we had a heavy lift vehicle. Earlier this year, we saw the return of the heavy lift vehicle, not as a Saturn V, but as a Falcon Heavy. Now, Falcon Heavy only has half the capability of the Saturn V in terms of lift, but it is 3/4 reusable. Okay? And the NASA is developing, albeit at a very slow pace, a heavier lift vehicle called the Space Launch System, the SLS, that'll have about 3/4 the capability of the Saturn V. And Elon Musk is developing a vehicle known as the BFR, which will have actually slightly larger capability than the Saturn V and be fully reusable. And by the way, that is how I think it should be used. I do not think that these cartoons that SpaceX has publicized of the BFR flying all the way to Mars, refueling it on Mars, and flying it back to Earth is a rational way to use that system. You would have to produce several thousand tons of propellant on the surface of Mars to refuel it to fly it home. It would take 2.5 years to get back, which means you would only be able to use it once every 4 years. And so there's a lot of flaws with that plan. But as a fully reusable Saturn V class vehicle capable of lifting 150 tons to orbit and then doing it again a few days later and again a few days later, what's not to like? So we are going to have heavy lift, and this opens up incredible possibilities. Now, so what's the plan then? Okay, this is what they call a mission sequence chart. Year 1 is not the year after Christ was born. Okay, year 1 is the first year of actual flight operations, and so in year 1, we launch a Saturn V class payload to Earth orbit. It could be an SLS, it could be a BFR, or 2 Falcon Heavies that do a maiden dock and then send the thing on its way. There's a couple of ways to do this, a couple of nuke links. But anyway, you launch sufficient launch capability to send a 40-ton payload on a one-way trajectory to Mars. Okay, Saturn V could do 140 tons to low Earth orbit, which means it could shoot about 40 tons to Mars. BFR could shoot about 140 tons to Mars. SLS, a bit less, maybe 30 tons to Mars. But you send a payload in this class on a one-way trajectory to Mars. It flies to Mars on what's known as a minimum energy trajectory. Takes 8 months to fly from Earth to Mars that way. That's the cheapest ticket there is. And then when it gets close to Mars, the payload, which is an unmanned payload, it's unwomaned too, there's actually no one in it at all. It opens up an aeroshell, and it uses that to make friction against the Martian atmosphere to capture itself from the interplanetary trajectory into Mars orbit. And then, after we check it out, and we check out the weather and make sure the coast is clear, we then bring it into the atmosphere deeper, and we use that aeroshell to plow us down to subsonic speeds. And then, after that has happened, we pop a parachute, and we come down slow And then when we get close to the ground, we use rockets to put ourselves down softly on the surface of Mars, just like we did with the Viking mission in 1976, or in a somewhat different style with the Curiosity mission in 2012, and are going to do with the InSight mission in 3 weeks from now. Okay. And so we've landed on Mars. What is it that we have landed on Mars? Well, the payload consists of a number of things. The primary object, though, is an Earth Return Vehicle, or ERV. Now, this is a little rocket ship from flying back from Mars to Earth. It's got, the top part there is the cabin, and that's a little cabin, 5 meters in diameter, almost 6 meters tall, so 2 decks with a little less than 3 meters of headroom each. Relatively tight quarters for a crew of 4 for a transit, 6-month transit from Mars to Earth in the final leg of the mission. But no one's in it now. Then below that, there's 2 rocket propulsion stages there that use methane, oxygen, rocket propellant combination. Methane's the fuel, oxygen's the oxidizer. However, they're not filled with methane oxygen. If it did, this thing would weigh about 6 times as much as it does. It'd be much too heavy for something like a Saturn V class rocket to shoot it to Mars. However, in some of the lower stage tanks that are later going to contain methane, we have about 6 tons of hydrogen, probably in gelled form. And then slung below the vehicle, not shown in this diagram, we have like a little pickup truck, like a little Datsun pickup truck. And sitting in the back of the truck is a little nuclear reactor with a power of 100 kilowatts. 100 kilowatts is like 130 horsepower. So we're not talking about a gigantic nuclear power plant like the WIPS plants that power a city. We're just talking about a nice little putt-putt nuke sitting in the back of the truck. And after you've landed, the truck is telerobotically driven a few hundred yards away from the landing site, unwinding a cable off the back of it as it goes. Okay? So, and then when we get a few hundred yards away, we put the reactor on the ground, preferably in a depression in the ground, like a little crater or a ditch, or just on the reverse side of the hill will do. Anything to put a nice sized chunk of dirt between the reactor and the main landing area so that it's shielded. And then we turn the reactor on. And now we have power at the ship, and we run a pump, and we suck in the Martian air, which is carbon dioxide gas. Okay? Everybody complains about carbon dioxide gas, but it has its uses. And Mars is 95% CO2. We can react carbon dioxide with hydrogen in the presence of a catalyst. It will turn into methane, that's CH4, water, H2O. That's reaction number 1 on that chart. Okay, methane is excellent rocket fuel. Okay, in fact, it's the rocket fuel the BFR is going to use and the new Glenn is going to use. It's actually the second most highest performing rocket propellant combination after hydrogen oxygen, but it's much more convenient to use than hydrogen, easier to store. So that's what we're making. So the methane we store in our tank, that's our fuel to come home. The water, reaction number 2. We split it, electrolysis, into hydrogen and oxygen, just as you may have done in high school. Oxygen is the oxidizer to burn the methane. The hydrogen recycles to make more methane. And then finally, to get the right amount of oxygen to burn the methane in the right ratio, we have a third reaction, number 3 here, in which we take carbon dioxide and we split it into carbon monoxide and oxygen. The oxygen we keep, that's what we need. The carbon monoxide we vent as waste. You can do that on Mars. There's no EPA there. It's out of their jurisdiction. It's great. Anyway, so although I must say that in the later phase of Martian development, not on the first mission, but later when we have a Mars base, you could use that carbon monoxide not as waste, but as a means of reducing Martian iron oxide to produce steel. Mars is red because of rust, because it's very rich in iron oxide. The way we produce steel on Earth is actually producing carbon monoxide by the incomplete combustion of coal, and then react iron ore with that. That's how we make steel. Well, you could do that on Mars too. But we're not going to do that on the first mission. So it's just dependent. But anyway, what we've managed to do here is take 6 tons of hydrogen brought from Earth and turn it into 108 tons of methane oxygen bi-propellant on the surface of Mars. That is a multiplier of 18 to 1. It's like a pioneer being able to acquire the useful mass of a bison for the transportive mass for a couple of bullets and cartridges. Okay? That's what makes the mission sing. 95% of the return propellant is being made from materials found on Mars. Only 5% had to come from Earth. And because we can make so much propellant, we make extra propellant. Beyond what we need for the Earth return vehicle, about 10% extra is made to provide a stockpile of methane oxygen to run ground vehicles using that as their energy source. Now, why do we want to use chemical energy to power ground vehicles on Mars? Well, the same reason why they're so popular here on Earth. They have much higher power to mass ratios than you get with electric vehicles running on batteries, let alone radioisotope devices. And that's why they're so much more popular here. And in a frontier environment on Mars, where you really do need the speed and the torque and the hauling capability and the all-around muscle that you have from having a real car instead of a golf cart, you really want to have one. But it wouldn't be practical to run such vehicles on Mars if you had to haul the propellant from Earth. But if you can make the propellant on Mars, then they are practical. And this is the other side of the equation. The ability to make use of Martian materials is not merely the key to making the mission cheap, it's also the key to making the mission effective, which is equally important because there's no point going to Mars unless you can do something effective when you get there. All right, so it took 8 months to fly to Mars. It took 10 months to make the propellant. That's 18 months. There's 26 months in between launch windows from Earth to Mars. So long before the next launch window has opened up, we will know we have a fully fueled Earth return vehicle sitting, waiting for us on Mars. Now, we are not risking the mission of stranding the crew if the propellant making doesn't work. It already has worked, past tense, before we have ever left Earth. Okay. That being the case, in year 3, roughly 2 years after the first launch, we launched 2 more payloads to Mars. One is another one of these Earth return vehicle fuel factory combinations. The other is a habitat spacecraft with a crew of 4 astronauts in it. Now, because our return ride is waiting for us on the surface of Mars, we don't need to fly to Mars in a giant Imperial Star Destroyer. We don't even need to fly to Mars in a comparatively modest Millennium Falcon. We can fly to Mars in a tuna can. And that is very fortunate, ladies and gentlemen, because tuna cans have been proven an excellent shape for packaging in commerce. Of course, our tuna can is somewhat larger than the chicken of the sea standard unit. This one it's 8 meters in diameter and 6 meters tall in the barrel section. So it's got 2 decks, each with 3 meters of headroom. The upper deck is where the people really live. The lower deck is more of a garage cargo hold kind of place. Here is one potential layout of the upper deck of the hab. And what you see here, okay, SR is stateroom. There's 4 staterooms for each of the 4 astronauts. There's a toilet area, as you can see, an exercise area, a science area, a galley area, a kitchen table to hang out. And in the center, that circle in the center, that's the solar flare storm shelter. Okay, now that's for radiation protection of a particular kind. There's 2 kinds of radiation that can get you in interplanetary space. There's solar flares and there's cosmic rays. They are entirely different in character. Solar flares come from the sun, and they come on an irregular, unpredictable basis. So you could have a big solar flare. Typically, you'd have a big one about once a year. Although you could have 2 inside of the same month and nothing much for 3 years. You're more likely to have them during a period of solar max than solar min. But the first approximation, there are events that happen with a frequency of about once a year and could hit you any time. And in the course of several hours of this big pulse of radiation from the sun, it can deliver 1,000 or 2,000 rems of radiation to an unshielded astronaut, which is enough to kill, either immediately or after a fairly brief period of radiation sickness. That's the bad news. The good news is that the kind of radiation that solar flares are made of are protons with energies of about 1,000,000 volts each. And that kind of stuff can be stopped with 5 inches of water, or things that from the nuclear point of view are essentially the same thing as water, such as food, or things that water and food become as the mission develops. And we have enough of that stuff on board the ship to pack it in around the limited central area there and create a shielded area, a pantry storm shelter. And so if a solar flare happens, the alarm bell rings, you go in there, you're packed pretty tight with your friends for a few hours, and then the all clear rings and you come out, and that's it. And that'll probably happen once during the mission. Conceivably, it could happen twice, but it's not a big deal. Okay. That would have been a big deal for Apollo, the Apollo missions to the moon, because they had no storm shelter. They were only week-long missions. They didn't have several tons of supplies on board to make a shelter with. But precisely because the Mars mission is it's a 2.5-year round-trip mission with 1 year of it spent in space, we do have a lot of supplies and we can build a shelter out of it. On Apollo, because it was a 1-week mission, it was improbable that there would be a solar flare during the mission, and they trusted to luck. And in fact, there was no flares during their missions. But if there had, they would have been toast. We, on the other hand, can shield ourselves with our provisions. So that's how you're safe against the solar flare on the Mars mission. Now, the other kind of radiation it can get you is of a totally different character. It is cosmic rays, galactic cosmic rays. And these are particles, they don't come from the sun. In fact, we don't even really know where they do come from or how they can come from anywhere, because they're particles that come into our solar system from interstellar space with energies not of millions of volts each, which is the typical energy of a nuclear reaction, like a fusion reaction that powers the sun, but billions of volts each, 1,000 times more energy, particle for particle, than you can produce with a fusion reaction. So we don't know how they're produced. They are impossible, but they are real. And they come into our solar system, okay, 1 billion volts apiece. You can't stop that with 5 inches of water. It takes several meters of water to effectively stop them. Okay? And we don't have enough mass on the ship to provide that degree of shielding. So you're going to take that bait. You're going to take that dose. Take the bait. You gotta take the toast. Sorry. Anyway, but the good news is the magnitude of the dose is not that big. It is around 50 rem for every year you're in space on the mission. Okay, now we're going to be in space a year on this mission. We'll be 6 months out, 6 months back. On Mars, we're going to be there a year and a half. But on Mars, you can have shielding. You have Mars underneath you that blocks out half the sky right there. You can put sandbags on the roof of the hab. You can do other things. And there is some atmosphere on Mars to help shield you. So that's not where you get the dose. You get the dose in transit. So we're going to get around 50 rem spread out over a 2.5-year period. Now, what is that? 50 rem spread out over a long period of time, like that, represents about a 1% risk of getting cancer at some point later in your life, assuming you're 35 years old and you're a woman. If you're a man, it takes a few more rems to give an equivalent threat because they're not vulnerable to breast cancer. If you're younger, a few less rems. Older, a few more. Older people are less vulnerable to radiation-induced cancer than young people for a number of reasons. One is that they're not growing, and the other is that they have less time to get cancer. There you go. But in any case, to first order, it's about a 1% risk, all right? Now, you're saying, oh, gee, 1% risk of getting cancer, I don't want that. Well, you have to put that in perspective. Right now, if you're a 35-year-old American, and you do not smoke, you have a 20% chance you're going to die of cancer. That's just how it is. this would make it 21. If you are a smoker, it's 40. So, in fact, if we recruited the crew out of smokers and sent them to Mars without their tobacco, we would be reducing their chance of getting cancer. So, one reason to send people to Mars might conceivably be for their health. Now, the other thing, and once again, because this stuff, in popular articles about Mars missions, it's constantly, how are we going to deal with the radiation problem? Well, let me show you something. We already are dealing with the radiation problem. The radiation cosmic ray dose in low Earth orbit is fully 50% of that in interplanetary space. The Earth's magnetic field protects the space station from solar flares, which otherwise we could protect from with the solar flare storm shelter if we're in interplanetary space. The cosmic rays, on the other hand, can zip right through the Earth's magnetic field. That's why you can detect cosmic rays on mountaintops. Okay. Now, the Earth blocks out half the sky as seen by the space station, and that's why it is a factor of 2 lower dose rate. But if you're one of these people here who have spent cumulatively, in some cases 700 days in space, in either the space station or the Soviet Mir, you can get cosmic ray doses fully comparable to what you would get going to Mars and back. And there's about a dozen of these people now. In fact, this chart's out of date because Peggy Whitson should be up there too. And there are no radiological casualties in this group. Nor would you expect it. Because if you got 10 people and they each have a 1% chance of getting cancer, chances are no one has. And then furthermore, it simply needs to be added. The space shuttle, the NASA people could say what they like about the risk of flying on the shuttle, but based on the track record, it's 2% chance you get killed on flying on the shuttle. Because 2 shuttle flights out of 130 were destroyed. Okay? And yet, who here, if NASA offered you a chance to fly on the shuttle, would take them up? I would. Okay? If you're not, that's fine too, but then don't volunteer to go to Mars. But, okay. So, and clearly a Mars mission, in terms of flight risk, launch, transit, re-entry, landing, Mars operations, return flight, and so forth, is going to be riskier than a shuttle flight. Okay. So the 1% risk of cancer is really a modest portion of overall mission risk, no matter how you do it. So the radiation is not a showstopper to Mars. And the idea that we should postpone the Mars mission until we have warp drive and can get there so fast that we don't have a radiation danger, to me is absurd. Now, there is, however, another phenomenon in space that has caused very clear health effects. And it's not radiation. It's zero gravity. Zero gravity, extended exposure to zero gravity, has very clear health effects. It deconditions bones and muscles, weakens the heart. It even affects vision and can cause various other symptoms. While you can certainly survive 6 months in zero gravity, in fact 6 months in the space station, that is the standard crew rotation for someone going to the station, to spend 6 months. And they all have survived it, but they come down weak. Okay, you've probably seen them being helped out of the capsules and so forth. The Mars Society, we have these practice Mars stations. We have one in the desert in Utah and another one in the high Arctic. And the people put on the spacesuits and they try to do field exploration as if they were on Mars. And the thing you learn on the very first time you do this is that doing field exploration wearing a spacesuit is a physical activity. Okay? It is not an extreme activity. It is not like climbing Mount Everest, but it's like heavy-duty backpacking. And that's what it's going to be like. And so you don't want to decondition the crew on their way to Mars if you want them to be effective in doing field exploration, right? Yeah, you can get to Mars, but if the purpose is exploration, that's not how you want to get to Mars. So I recommend artificial gravity. And we can create artificial gravity for the crew. You can see what's going on here. The thing on the left here, that's the upper stage of the booster that threw them to Mars. So it's coasting out to Mars too. It no longer is functional except that it can serve as the counterweight on the end of a tether. And if this tether here is about a mile long, we spin this up at 1 revolution per minute, we create Mars gravity in the hand. If we span it at a little less than 2 revolutions per minute, we could create Earth gravity in the hand. And that's how we avoid the long duration effects of zero gravity. And I believe that, it's a scandal that there has been no experiments done with this at all at NASA or the Soviet program for that matter, despite 60 years of spaceflight. There has not been a single capsule that they've launched and made to spin and put a crew of mice in it to see how they would do in Mars gravity or anything of the sort. But we, soon they're going to have dragons flying to the space station, and you could take the upper stage of the Falcon rocket and the Dragon and tether them off and spin the thing up. It'd be just like this, and you could test out this system that way, and I think they should. Both to learn about artificial gravity and also about 1/3 gravity, which is something we want to learn about before we go to Mars. So, they're flying to Mars on a 6-month trajectory. That's a little faster than the minimum energy trajectory. The minimum energy trajectory, you may recall, is it was 8 months. Put on a little extra juice, you can get there in 6. Now I say put on some more, you can get there in 5. Okay, why not 4? Well, first of all, there's 2 reasons. It doesn't take that much extra propellant to cut a little bit of fat off the trip time and get there in 6 instead of 8, so fine. You start trying to go there even faster than that, it starts really costing you. And what it's costing you then is, for a given launch mass, you have to get rid of payload, okay? And you're actually becoming less safe with a less redundant life support system, less backups for this, less backups for that, then you're benefiting by trying to go a bit faster. That's one reason. But you might say, okay, fine, I get that, but why do you say 6 months? What's wrong with 5.5 or 6.2? Okay, well, there is a peculiar thing about the 6-month trajectory, which is that it is the trajectory that if you decide when you get close to Mars that you're not going to land, you can fly past Mars, and you go out to about 2 astronomical units, that is twice the Earth's distance from the sun, and you loop back and you reach 1 astronomical unit, the Earth's distance from the sun, precisely 2 years after you left. So guess who's there to meet you? The Earth, which has gone around twice. If you had tried to get to Mars faster, you would push further out into the asteroid belt and you'd come back a bit after 2 years after you left, and you miss the home planet. If you'd go slower, you'd get back sooner than 2 years and you'd miss the Earth. So this is what's known as the free return orbit. And this is therefore the right way to send people to Mars. There are people going around saying, I got this more advanced propulsion system that I'm developing, and this can get you to Mars in 4 months instead of 6. If I had that propulsion system, I would not use it to get to Mars in 4 months. I would simply use it to increase the payload and still get to Mars in 6 months. Because the free return orbit is of singular value. Now, anyway, they're flying to Mars on a 6-month trajectory. When they get close to Mars, and by the way, the InSight probe that is now approaching Mars, okay, it's November, it was launched in May. 6-month trajectory. Now that was not done because it was a free return, because it was an unmanned probe, and not interested in free return, but it was simply done because it was a good trajectory. But if people tell you it takes 2 years to get to Mars, that's simply untrue. Okay, we're getting to Mars in 6 months this year, right now. Anyway, 6-month trajectory to Mars. We get close to Mars, we fire a pyrotechnic device that cuts the cable, so the upper stage and the tether go away into interplanetary space, and the human spacecraft comes sledding into the atmosphere, aero brakes into orbit, check out the weather, check out the systems, and then if it's good, they come in and they go and they land at landing site number 1, where the fully fueled Earth return vehicle is waiting for them. Now, we've been on the ground at landing site number 1 for 2 years. We have thoroughly explored the area with little robotic rovers identifying all the hazards. We put a radar beacon on the ground to the best place to land. Okay, we have an expert pilot and aces flying this thing. He's going to land right on the spot. You are there. And some of you may even remember, and others may have read, that during the Apollo program in 1970, we actually landed an Apollo lunar lander within 200 yards of the Surveyor robotic probe that had been put on the moon a couple of years before. And we've got much better guidance systems now. So we're going to land right there. Okay. But let's say you don't. Let's say for some reason this just doesn't work, and you land 30 kilometers off course, 50 kilometers off course. These would be spectacular landing errors. Well, we're okay, because we have with us in the lower deck of the HAB a pressurized ground roving vehicle, about the size of a small SUV. And it runs on a methane oxygen engine. And it has a one-way driving range of 600 kilometers. So it would really take piss-poor piloting on the part of the pilot to land outside of the radius of action of such a vehicle that is further away from the designated landing site than that. But let's say that fails too. Let's say instead of landing 100 kilometers or even 500 kilometers away, they land 5,000 kilometers away on the wrong side of the planet. I mean, that would represent a very serious problem with the pilot selection process at Johnson. Well, if that were to happen, you can still save the mission because you've got another Earth return vehicle following you out to Mars on the 8-month trajectory. And if you land on the wrong side of the planet, they can bring that one down to land near you, wherever you did land. And that wouldn't be done correctly because it'd be automated. And now in that case, you would be depending upon the chemical synthesis apparatus to work in real time instead of prior to your arrival. But the success of the technology has already been demonstrated by the success of the first lander, and you do have a human crew on the scene to fiddle with the gears should it malfunction while they are there, although in this particular example, you would not want the pilot to take part in that activity. But nevertheless, this is a pretty good third-level backup. And finally, if all that fails, if you cannot land accurately, if you cannot drive there, if you cannot use the second Earth return vehicle, the fourth-level backup is that we have the whole crew landed on Mars where they have natural gravity, where they have substantial radiation protection offered by the Martian environment, and they've got enough supplies with them to last for 3 years. So if worst comes to worst, they just tough it out on the surface of Mars until the next launch window opens up and more supplies, another Earth return vehicle, can be shot out to them then. So what we have on this mission is a 4-layer defense in depth, that is 4 layers that actually involves carrying off the mission as well as 1 abort option. So it is as safe as it's going to be. Okay. Now, however, of course, we really don't want to use the second Earth return vehicle for us. If this thing works the way it should, and we land at landing site number 1, and we check out the vehicle, we already had automated health checkout on it before we ever left Earth and all that, but now we can go there, we can kick the tires, make sure everything's square. What do we do with the second Earth return vehicle? Well, we land it somewhere else, where it will start making propellant to support the next human mission, which will fly there in year 5, along with another Earth return vehicle, which is their backup, but which otherwise opens up landing site number 3. So the idea here is that every 2 years, you're launching 2 boosters to Mars. 1 to open up a new site, 1 to exploit the site that was open 2 years before. 2 boosters every 2 years is an average of 1 per year. When we were launching the shuttles in a serious way, it was an average of 6 a year. So we're talking about using 1/6 of our heavy lift capability to support this program. That means that this program doesn't have to hog the whole heavy lift program. We could also be doing the moon at the same time, asteroids, both. Okay, so this is a Mars program that is sustainable within the context of a human spaceflight program that is achieving multiple objectives simultaneously. There you have it. This is an actual photograph of the Mars base. Yeah. Okay. You can see the conical spacecraft is the Earth return vehicle, the Tunican is the HAB module. The reactors in that crater in the background. There are some photovoltaic panels over there, which the crew sets up, that gives them backup power if they ever have to turn the reactor off. You can see the exploration vehicle, a little pressurized rover over there, that can also provide backup power by running its engine. The light truck is in the shadow of the Earth return vehicle on the far right. And in the foreground, you see an inflatable greenhouse, which is not a mission-critical element. It's an experiment in growing crops on Mars, in Martian soil, Martian water, Martian sunlight, Martian gravity, for the benefit of future missions and future bases. Now, we're going to be on Mars for a year and a half. Why a year and a half? Well, actually, you do have a choice. There's actually two mission plans. One that spends 20 months in transit and 1 month at Mars, gets you home in 21 months, but you only get to spend 5% of the total mission plan on Mars. I do not approve of that mission plan. I think it's absurd. But this plan, you're 6 months out, 6 months back, 18 months on Mars, so it's a total of 30 months. But 60% of it is spent on Mars, and that's the productive part of the mission. Okay, the only merit of the other plan is that it provides minimum time away from Earth. But if your figure of merit for designing a Mars mission is minimum time away from Earth, you shouldn't leave. The idea is maximum exploration for the effort. So that's why this is. So if you're taking the trajectories that I have discussed, which are, for, believe it or not, astrological reasons, known as a conjunction class mission, whereas the other, for astrological reasons, is known as an opposition class mission. The terms are that ancient. But you fly in conjunction. You have to wait a year and a half for the planets to move around to give you the launch window to go back. But it makes sense. If you're going to Mars, spending 60% of the total mission time on Mars is reasonable. Now, what are we? So we're going to explore. We're going to have time to explore. We're going to explore. Okay, what are we going to explore for? We can explore for all sorts of things: geology, mineralogy, meteorology, etc. Learn this and that about Mars, and a lot of professors are going to get publications in tenure, and it'll be great. But there's two fundamental sets of questions that we're interested in exploring Mars for that are of interest not just to professional planetary scientists seeking tenure, but to the human race at large. And the first set of questions revolve around the issue of was there or is there life on Mars? Okay. Because, well, this is a real photograph of Mars. This was taken by the Viking orbiter in 1976. And what you can see here are dry riverbeds on Mars. There are no canals on Mars. That was a telescopic illusion. But there really are dry riverbeds on Mars, and plenty of them, and whole networks of them, and dry lakes, and a dried up ocean, and that we have found since this photograph was taken. And now we even know that there are underground liquid lakes on Mars today. But there was liquid water on the Martian surface in quantity for 1 billion years during the planet's early history. We can tell that from examining these erosion features. Okay, that's how long it took to create this stuff. That is 5 times as long as it took life to appear on Earth once there was liquid water here. 5 times as long. So if the theory is correct that the development of life from chemistry is a natural consequence of chemical complexification wherever you have the right climatic conditions and appropriate set of chemical elements, and all the chemical elements we have on Earth, they have on Mars, and all that, If life is a natural consequence of chemistry occurring with high probability wherever you have appropriate conditions, cause and effect, then life should have appeared on Mars. Even if it subsequently went extinct at the surface, and we'll come back to that in a second, when conditions deteriorated. And if we can go to Mars and hike around this landscape and find fossils of the past life on Mars, we'll have proven that the development of life from chemistry is a general phenomenon in the universe. And since we now know from Kepler that planets that are of this nature are a general phenomenon, 1 in 5 stars, we look up in the sky, okay, they're out there, billions of them. We've got billions of inhabited worlds. And since the whole history of life on Earth is one of development from simpler forms to more complex forms, manifesting greater capacities for activity and intelligence, and in fact ever more rapid evolution, because the ability to evolve itself is adaptive. If life's everywhere, it means intelligence everywhere. It means we're not alone. This is something that thinking men and women have wondered about for thousands of years. This is worth finding out. Now, furthermore, since we now know that there's still liquid water underground on Mars, if there was ever life on the surface, if we can reach that water, it's probably there. You know, the original inhabitants of the Earth, the first microbial life on Earth, can no longer live on the Earth's surface because the early Earth had no oxygen in its atmosphere. It was created by photosynthetic organisms. And by so doing, they radically changed the Earth's surface environment. And for the original inhabitants that were here, that represented pollution, fatal pollution, toxic pollution. And they had to go underground. Okay, the original anaerobic microbes that were the first life on Earth no longer could live on the surface. They could only live underground. And they're still in the groundwater today. They've been down there. They've watched everything on the surface come and go. They watched the trilobites come and go, the dinosaurs come and go, the mastodons, the Wehrmacht, all this stuff, you know, that it comes, it goes, goodbye. Okay, we're still here. And they'll be here after we're gone too. Okay, well, if there was ever life on the surface of Mars, when the surface deteriorated, it would retreat down into the groundwater, just as it did here. And it would still be there today. And if we can send human explorers, we can set up drilling rigs and get down there. It's about 1 kilometer down. We have drilling rigs here that go significantly deeper than that. Bring up that water, see what's alive in it, and see what it is like. And this is really interesting stuff. Because you see, all Earth life is fundamentally the same. Even these early critters that can't exist on the surface anymore. They all use the same amino acids. They all use the same method of encoding information, RNA and DNA. In other words, they all use the same alphabet. And now you think about this. Okay. Here in North America, okay, we speak English, we use the Latin alphabet. Mexicans speak Spanish, they use the Latin alphabet with a couple little differences. Quebecois speak French, Latin alphabet. But if you go a bit further abroad, you go to Russia, they use the Cyrillic alphabet. That's a different alphabet, okay? So if you travel a little further out, you can find out there are alphabets that are not like ours. Well, of course, the Cyrillic alphabet is different than ours, but it actually shares a common origin, and the fundamental principles of how it operates are the same. That is, it communicates information not by describing things, but describing sounds that represent those things. Okay? Which is the Phoenician system. But the Chinese system doesn't describe the sounds of things, it describes the things themselves. It uses pictograms that are ultimately based on how things looked. Same with Egyptian hieroglyphics, but an entirely different type of pictogram than the Chinese version, and so forth. So the question is this. All life on Earth uses the same alphabet. But does all life use the same alphabet? Does everybody use the Latin alphabet in the universe? Or some of them use Cyrillic, and some use Chinese, and some Egyptian hieroglyphics? In other words, is life as we know it just... Is it what life is, or is it just one peculiar example drawn from a much vaster tapestry of possibilities? This is really worth finding out. And we could find this out by bringing up that water and seeing if those critters use our alphabet or a different alphabet. So there you go. Now, by the way, there's another thing, because there's a lot of articles been coming out recently, in pretty strange quarters, sounding the alarm. Elon Musk might go to Mars. It will ruin the search for life on Mars. If humans go to Mars, we will never know if the life we find there was there before or was brought by us. Well, this is just wrong, and I'll tell you why it's wrong. Okay? First of all, if we go to Mars and we find life that's fundamentally different from us, if it uses a different alphabet, then clearly we didn't bring it. If we go to Mars and find life that is superficially different than us, that is, it uses the same alphabet, but it's different kinds of microbes than we've ever seen before, different particular types, then also we didn't bring it. Okay, what if we go there and all we find are the kind of microbes that use the same alphabet as us and we in fact have seen before on Earth? Okay, E. coli. How do we know whether we brought it or not? It's simple. If it's native, it has a past on Mars. If it's native, it was not, if it's native, it was there before you were there, by definition, and therefore it will have left fossils. And unless you're one of these people that believe the planets were created with the fossils in them so that God could fool us into thinking that evolution really happened when in fact the world was created in 7 days complete with dinosaur fossils, okay, you have to admit that if you find life on Mars today, as well as biomarkers indicating that it existed there in the past, it's native. On the other hand, if all you find on Mars are microbes identical to those that we see on Earth, and there's no evidence that they existed in the past, then yeah, you brought them. That's all there is to it. So, if we send people to Mars, we can absolutely tell whether the life forms we find there were brought by us or whether they were native before us. Okay. And, of course, the idea that we'll know more about Mars by not going than by going is absurd. The planet we know the most about by far, of course, is the Earth, because we're here. And same with Mars. Anyway, if we do this and we bring up that water, we could find out the truth about the potential prevalence and diversity of life in the universe. Now, after a year and a half on Mars, it's time to leave. So we get in the Earth return vehicle, that mechanical vehicle over there. We start it up, take off, we fly back to Earth. We leave behind on Mars the habitat, the vehicles, the greenhouse, the reactor, the solar panels. Leave all that stuff behind. Now, is that bad, leaving all this very expensive aerospace, advanced technology behind on Mars? Shouldn't we bring that stuff home with us? No. We have a lot of stuff here already. The idea of Mars missions is to go to Mars with as much stuff as you can and come back with as little as you can. Because all the stuff you leave behind on Mars becomes available for future explorers to use. So, here is, this is a map of Mars. Texas is there for scale. Each of these missions, it has the ground vehicle has a one-way range of 600 kilometers, so it has a sortie range of 300 kilometers. And if the centers, did I say kilometers? I meant miles, actually. It has a sortie range of 300 miles. Here is a pattern, a landing pattern, which is somewhat arbitrary. I mean, it's a plausible one, but lots of others could be come up with. The landings are at the centers of the circles. And Texas indicates the size of those circles. Each circle has a radius of 300 miles. So with a year and a half and a ground vehicle that can do a lot of traveling, you could explore the interior of one of those circles. Okay. Now, of course, if you're stuck in Texas, you probably want to go to a different circle. And so you can drive, since the centers are offset by 500 miles, you could drive from your Texas base to your New Mexico base, refuel there, and continue to explore in a more interesting state. Or wherever. Okay, anyway, the point is we're opening up territory on Mars on a pretty substantial scale. Now, after a number of these missions have occurred, and I don't know whether it's 8 or 6, or whatever, but a certain number like this, you're going to know. You will have found fossils or you won't have found fossils. You'll have drilled down to water and found anything in the water or not found anything in the water. We're going to know the answers to these questions of is there life on Mars, and what it's like, and how far it managed to get. That being the case, the agenda is going to shift. Because you may recall I said there's two fundamental sets of questions. And the second set is even more important than the first. And that is not was there or is there life on Mars. That is, will there be life on Mars? See, because the most important single fact to know about Mars is this, that Mars is not just an object of scientific inquiry. It is that. It's a very important one. It's the Rosetta Stone for letting us know the truth about life. But it's more than that. It is a world. It is a planet with a surface area equal to all the continents of the Earth put together that has on it all the materials needed for life and therefore technological civilization. And if we can go there and learn how to turn those materials into resources, then we can make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet? You know, like in Star Trek II, The Wrath of Khan, where at the end, after they get rid of Khan, they terraform a planet and turn this barren world into this lush, wonderful planet that is covered with forests and meadows and butterflies and chipmunks and flying fish. Yes, of course. That is exactly what I mean. I actually believe, it's the correct term, believe, that humans will do that with Mars someday. And the reason why I have faith that we will do that is because we're life. And it is the nature of life to take barren environments and transform them into those that are friendly for the development and propagation of life. That's the whole history of life on Earth in a nutshell. That's why life here has been a success. Life has radically transformed the Earth to make it a much better place for life. Life put oxygen in the atmosphere. There are those who didn't like that. They went underground. But for the rest of us, this was really an improvement. And it made possible complex animals and the plants that go along with them. Life created the soil on the continents. Life colonized the continents. Symbiotic communities of plants and animals started up the seashores, up the plains, up the hills, up the mountains, as high as life can go, it goes. And no sooner does a barren place appear on Earth than life moves in and transforms it. We think of Hawaii coming out of the ocean, bare peace, sterile basalt. The birds fly over and they drop seeds, so the place becomes lush. And then Polynesians show up and let loose pigs, so there's something really good to eat. And then Europeans show and they build first-class hotels, so there's a good place to check in. Okay, this is what we do. Okay, it's what we do. And I believe that it is unnatural if humans, as the kind of bird, as it were, that the biosphere has evolved to take the seeds of life from this island to other currently barren islands out there, did not do exactly that. And so I believe that we will do that someday. But that is not what we are going to do here. Okay, we who are in this room tonight, that's beyond our time. That's going to require abilities beyond those that we can expect to create in our time. But what we can do, we who are here tonight, is transform Mars in a different sense. Not physically, but intellectually. Because the thing that defines whether an environment is habitable or not is whether you can turn the materials there into resources. Okay? There is no such thing as a natural resource. That's a complete mistake. There are no natural resources. There are only natural raw materials. It is human creativity that turns materials into resources. You take land. Okay, people think, oh, land's a natural resource. No, land is not a natural resource. Land is only a resource because people invented agriculture. Before we invented agriculture, it was just something that got in the way of chasing deer. Okay, And then, of course, by advancing agriculture, we've multiplied the actual magnitude of that resource many times over. And oil. Oil is not a natural resource. No one thought of oil as a resource before 1859. When we developed oil drilling and then ways to refine it for, first for lighting, kerosene lamps, and then various kinds of machines such as automobiles that would run on the product, distilled product that was made from it. And now it's a fundamental resource of our society. Before that, it was just the stuff that came out of the ground and ruined your farm. Uranium, not a resource until we develop nuclear power. Deuterium is not a resource now, but it could be once we develop fusion power. Okay. Anyway, the point is this. We developed the craft of turning Martian materials into resources. Okay. Mars Direct begins that process by knowing how to make fuel and oxygen on Mars, but we have to go beyond that. We have to learn how to grow plants on Mars, yes. Extract water, extract geothermal heat from the surface from the subsurface to make power, to learn how to make bricks, ceramics, metals, plastics, wires, tubes, habitation structures. If we can move up that progression of craft, then Mars becomes for us a place where humans can become self-sufficient and where new branches of human civilization can therefore develop, which in the fullness of time will grow in size and population and industrial capabilities and technological know-how to the point where it can actually seriously address the question of transforming Mars. So we don't just bring life to Mars, we bring Mars to life, which is the program. That's the program. And so, there we are. It's the first planet that we can transform. It won't be the last. Once human beings are settled on Mars, it's the beginning. Columbus crossed the ocean in ships that even a generation later, no one would attempt to cross the Atlantic in. He crossed the Atlantic in ships that were rated for the Mediterranean, for inland sea, for coastal navigation. No one had developed transatlantic capable ships. There was no purpose of them. But once European civilization became transatlantic, the Columbus's little boats were replaced by three-masted caravels, and then you have the ships of the age of fighting sail, and clipper ships, and steamboats, and ocean liners, and Boeing 747s, okay? And which incidentally were invented by the new civilization that was created on the other side of the Atlantic. But in other words, the first people that go to Mars will go in tuna can habitats. Okay, but their grandchildren will travel in fusion-powered spacecraft that will do the trip not in 6 months, but in a month or something. And they'll wonder at the tales of their grandparents of how it was when they made the passage, just as some of us did with our grandparents and their immigrant stories. And because, we travel the ocean in a day. So there you have it. And so there's the same technologies that make traveling to Mars a matter of a business trip will make adventurous colonization of the outer solar system possible. And the same technologies that make the outer solar system tame will make interstellar voyages possible. So we're moving out. And I believe that if we do this in our time, okay, that we establish that first human foothold on Mars, okay, that 500 years from now, okay, who could imagine all this when Columbus made his voyage 500 years ago? Okay. But 500 years from now, there will be not only new branches of human civilization on Mars and on thousands of asteroids and the moons of the outer solar system, but on thousands of planets orbiting stars in this region of the galaxy. And when they look back at this time, what will they consider most important? Which gang of thugs took power in Syria, which gang of thugs took power in Washington, so forth. you know, the issues of the day. Most of them won't know who these people were, okay? But looking back at this time, they will wonder at us because this is when humanity first set sail for other worlds. And so we're living at what future ages will regard as the beginning of history. And I suggest we get on with it. Thank you. I'd be delighted to take questions. They're in the Grace letter.
There's been a number of articles written about if we're not alone in the universe, where's the rest?
Okay.
And at the speed we're moving, it seems like other people should be doing the same thing.
All right. Well, okay, so it's a complicated question. Where are they? All right. And are we them? Because, well, let me break it down for you. Okay, there's a effort to try to detect alien civilizations known as SETI, searching for radio signals that they might be emitting, and using perhaps for interstellar communication. This program was initiated by a man named Frank Drake back in 1960. Frank concluded that I think it's the 21 centimeter band of radio was the most logical frequency for aliens to use. And he set up a radio dish and he looked at TOS Ceti and to see if they were transmitting in this 21 centimeter radio band, which conveniently was also the radio band that the early space program was using itself for space communication. It's known as L-band. And he didn't find anything. But he made a bit of a splash, and people were inspired, and larger efforts were mounted, and the SETI Institute was founded, and eventually got millions of dollars, mostly from Paul Allen, to build large arrays to look for these L-band transmissions. Well, guess what? We don't use L-band anymore for our space communications. It's obsolete. That is, within a half century, we use X-band, and in fact, we're moving on from X-band to a still higher frequency, Ka-band communications, which the SETI Institute isn't even looking for. And it's pretty clear, by the way, that why aliens would not use L-band, or even X-band, or even Ka-band, because for instance, if you take the Mars Reconnaissance Orbiter, which is a first-class spacecraft orbiting Mars right now, communicates back to Earth in X-band, okay, which is the current state of the art, and it can do 6 megabits a second. That's pretty good. If you put it in TOS Ceti, it would do 6 microbits a second. That's pretty slow, okay? That's a couple of hundred bits a year. That's an impractical method of interstellar communication. Now you say, well, okay, well, it has 100 watts. Why not give it 100 gigawatts? It would still be pretty damn slow. And who would want to be shooting 100 gigawatts of radio transmission at an unknown planet? And furthermore, if you're communicating among yourselves, in other words, let's say you're a wildlife biologist and you're in Africa, okay? Do you communicate with your colleagues with bullhorns so that the lions can hear you? Okay, well, you might use walkie-talkies, but then the poachers can hear you, okay? You're more likely, if you can, to use one of these, which is encrypted, and you keep your communication private, okay? So the idea that aliens can be communicating with among themselves with bullhorns, or that they'll be using a technology that was obsolete within a few decades of when it was proposed as the state-of-the-art method of space communication. It's like, I flew here a couple of nights ago, and I looked down, And I did not see the spectral signatures of any of the gas lights of Seattle. Where are you people? What happened? Okay, we found the ruins of the Gaslight Park. Civilization's gone. But in other words, it's a transitory technology. So I think that in terms of trying to detect aliens, you're unlikely to detect them by looking for their comm signals. Okay, I'll tell you how I think we will find them. Okay, I think we may find them within the decade of the 2020s or so with space telescopes looking for the spectral signature of oxygen in the planetary atmospheres of exoplanets. Oxygen is an artifact of life. There was no free oxygen in Earth's atmosphere until there was life here, okay? Because oxygen is very reactive, and only the anti-entropic activity of life, of basically undoing chemical equilibrium and putting the oxygen out in the atmosphere, can make an oxygen atmosphere. Say, okay, so you see oxygen, well, that proves there's life, it doesn't prove there's civilizations. But what if we then look around and we say, well, on average, 1 in 100 stars, or whatever the number is, has a planet with an oxygen atmosphere. Except in one particular region of space where 1 in 2 do. Well, that would indicate that there are somebody there spreading life, that there's someone there who's running around terraforming planets in that particular region. In other words, I think the way we're going to detect ET is by looking for their large-scale works, such as terraforming planets. Conceivably, if they're using very high-powered spacecraft, you might be able to detect the emissions from such things, and I've written a paper on that. But I think their largest-scale works will be terraforming planets, and if we can find places where there are concentrations of living worlds, that would suggest that there's intelligent activity there. And in terms of the somewhat strange comment I made, you said, how do we know we're not them? There's a question about life on Earth, which is that we find no simpler free-living organisms than bacteria, fully armed with the full Latin alphabet of DNA, RNA. Okay, that is, they may seem simple to you, but they have a very sophisticated method of genetic information encoding. Could that really have been the first life? Now, you could say maybe it was, and they just wiped out their more primitive ancestors, but that's not the general pattern we see in the biosphere. The general pattern we see in the biosphere is that as more advanced organisms evolve, the more primitive species continue. Okay. So is life on Earth an immigrant phenomenon? Could it have been transmitted by accident? Could it have been transmitted by intent? Who knows? But anyway, I think they're out there. I mean, of course, that's just a matter of belief, but my general belief is, as above, so below. Or put it another way, well, 1600, the Italian philosopher Giordano Bruno took a step beyond Copernicus and said, well, okay, the Earth's going around the sun, and so are the planets, and I tell you what, I'm guessing that those stars are suns. And if they are, then there's planets going around them. And then there's people on those planets, just like here. And when they look up in the sky, they see our sun as a star, and therefore, from their point of view, we are in heaven. Now, the Inquisition didn't appreciate this, and they burned him at the stake. But, think about it. The Earth is in space. So, we are an extrasolar planet. Okay, that's what we are. And if we have life, why not all the other extrasolar planets? Other questions? Red switcher.
So will the flight back in the ERP be in a ERP environment?
Well, it can be, and when we originally designed this mission, that's what we did, because we figured that So what? They get deconditioned on their way back. They don't have an exploration mission in front of them. All they got to do is sit around on the beach, drink martinis, sign advertising endorsement contracts, that kind of stuff. But if you wanted to, you could do it with using the same general technique. Other questions? Over there.
As a research scientist, how do you balance the ethics of the possibility between like being receptive to new spaces and conversely kind of rusting quite literally on preconceived knowledge and patterns? I mean, most of our past colonizations have resulted in a decrease in biodiversity rather than an increase per square mile or per square area.
Okay, so you're looking at this from the point of view of how this program will affect biodiversity. The what?
I guess more generally, just awareness of space and definition of space in terms of, like you discussed, leaving those units behind, which is useful in reusing them, but it's also, I think, the principles of leave a trace, and there's also the potential for detriment or contamination.
Well, okay, there's potential for everything, but okay, look, here's what best answer I can give. Okay. Every act of creation is an act of destruction. Okay. Michelangelo made a statue. He groomed a perfectly good virgin block of marble. Okay. And of course, well, let us take the very controversial Christopher Columbus. Okay, used to be more popular than now, but look, when Columbus landed here, not exactly here, but in the New World, let's take North America. Okay, we had this incredible wilderness. We had herds, 60 million bison, Native American cultures, towering redwood forests, and all that. Now, as a consequence, not due to him personally, but in terms of the set of events he set in motion, that was replaced by what we have here now. We have a continental nation of 300 billion people with hundreds of cities, universities, used bookstores, and space museums, and all of what we have in America. So something was destroyed, something was created. That's what happened. And reasonable people can differ as to whether more was created or more was destroyed. Okay. I happen to believe a lot more was created. 300 million people living in liberty and all this, and civilization that pioneered human rights and telegraphs and aeroplanes and all sorts of things. But it is certainly true that there's a significant element of tragedy here because something grand was also destroyed in the process of doing it. However, I submit to you that if there had been nothing here when Columbus landed, but a vast desert with nothing in it but maybe a few microbes under the ground, that nobody would be picketing Columbus Day parades today. So, while I understand your concern, I say that on Mars, there's much less to destroy, and on Mars, we have the ability to create with clean hands. And in creating not only a civilization on Mars, but a biosphere, I mean, think of it. We will bring with us all this abundant, well, not necessarily all types, but many types of plants and animals from Earth. And if they're on Mars, they're going to evolve in new directions. Because even if you terraform Mars, give it an oxygen atmosphere and everything, it will still have 1/3 gravity. So animals, plants, humans, they will all evolve in new ways. Okay, there will be new species, new forms of life. We are going to create vast new biodiversity on Mars. And So I think that it would have to be looked at fairly as a tremendous act of environmental construction. I absolutely disagree with people who think that any alteration that people make to the environment is, by definition, bad. If we can make an environment worse, we can also make it better. Okay? It cannot be the case that no matter what we do, it's wrong. So, I mean, any real environmentalist, or I don't know, anyone, frankly, who's not totally nuts, if I propose to you that, hey, I got a great idea, let's make the Earth as it is like Mars, because I think it's kind of cool, you'd say, you're out of your mind. You want to turn this lush planet with all the stuff we have here into this stark desert with a few microbes in the water under the ground? You're a madman, okay? Not even Hitler would conceive of such a thing, right? It'd be the most incredible act of destruction you could imagine. So, fine, okay? Left, right, center, I think we can all agree on that. Now, therefore, if someone comes along and proposes to do the exact opposite of taking a dead or near-dead world like Mars and turn it into a place like this, if the first was the ultimate evil, this has to be the ultimate good. Over here, sir.
So SpaceX has made aspirational the date 2024 for a significant landing, maybe something in 2022 to send cargo. What are their odds of pulling that off, and what do you think the biggest challenge of them being successful?
I think the odds of that are maybe 1%. But the look, Elon Musk frequently promises to do things bigger and certainly sooner than he actually can do them. But at the same time, it must be admitted that he does do a lot, and he eventually. Okay, Falcon Heavy took longer for him to develop than he said it would, but he did it. Now, it also has to be said that Elon skates pretty close to the edge of the ice. Okay. He is a risk taker. And of course, he would not be as rich as he is today if he wasn't a risk taker. But one might also remark that even the most successful risk takers sometimes take one risk too many. And, you know, even a talented general like Napoleon Bonaparte eventually blew it, right? After a string of victories. So it's possible that Musk might skate off the edge of the ice. Okay? There's no guarantees here. But if he doesn't, I actually believe that SpaceX will send people to Mars by 2030. Not by 2022, no, that's too soon. But by the end of that decade. The way he is moving around, he's moving fast. He's moving fast. Now, he's not moving as fast as 2022, but he's moving pretty damn fast. And I've been there, and yeah, they are building components of the BFR right now. And so it'll take a bit. I also think that the way the BFR will be used ultimately will not be flying the whole BFR to Mars and refueling it to fly it back. I think it'll be used in a somewhat more conventional way as a fully reusable Earth-to-orbit launch vehicle. If you can refuel it on orbit, it might make sense to fly it out about as far as translunar injection, that is a highly elliptical orbit just short of Earth escape, stage the payload off of it there, return it, it gets back to Earth orbit a week after it left instead of 2.5 years, so you get to use it many more times. But he'll figure that out. I mean, I know Musk, you know, and he is a person, it's hard to get him to change his mind, but when presented with the facts and the realities, he can make adjustments. He starts out with very grand concepts, and he basically says, show me why we can't do it this way. And he pushes it to the limit. And so that's why and he's certainly very strongly motivated. And I think people here, since he is so newsworthy, you might want to know what my impression of him is as a person and all that. He is a very interesting person, obviously. He's not Mother Teresa. He's not a kind person. At the same time, he has an ethical basis. And he's not an egomaniac, although sometimes he may give that impression, but that's not what is driving him. And he's certainly not driven by money. Although he likes money, he finds it useful, he finds it essential, okay? And he's very good at making it. But what he is actually after, if you want to know my take, is what the ancient Greeks called kleos, which is eternal glory for doing great deeds. That is his motivation. That's what he's in it for. He's not in it for the money. He's not in it for cheap fame of the Paris Hilton variety. Okay? He's not in it for doing great deeds as such, unless he gets the credit for them. That is, he wants eternal glory for doing great deeds. Okay? His motivation is the same as Achilles. He's a Homeric hero. That's what he is. Or a better example, actually, is Henry V in the Shakespeare play, who is happy that there aren't other people there to share the glory of Agincourt. Right? Not one man more would I have here. Okay? That's why he doesn't play well with others. Okay? It's why he was so upset that somebody else got to rescue the boys in Thailand. Okay? But he's not Donald Trump. Okay? If you went to Elon Musk and said to him, I have a great plan for you to make a fortune building a casino strip joint in the Virgin Islands, this is absolutely guaranteed to make money, and in fact you had all the numbers, and in fact it really would, he'd throw you out of his office. He's not interested in that. Okay? He wants, so if you look at the things that he's into, trying to open the space frontier, and solar power, and electric cars, these are all areas that he thinks are the key breakthroughs to advance human civilization at this point in history. That's why he's in those fields. Okay. So, eternal glory for doing great deeds, you can say it's not exactly a pure motive, but it's the motive that motivates heroes. Okay? Not heroes in the sense of ideal people, but heroes in the Homeric sense.
I think we'll take one more question.
Okay.
So we'll have time for the book signing.
All right, in the white shirt.
What do you think will colonize after Mars?
Well, I think we'll do the moon at about the same time as Mars, and then after that, the asteroid belt. Okay, so I guess I have to take, let's do the book signing.